Okay. By the end of this video, you should be able to explain the relative resistance to bromination of benzene compared to alkenes, describe the reaction of phenol with bromine, and explain the relative ease of bromination of phenol. Okay, so phenol, something we haven't met before. I'll explain that when we get to it. And so we're looking at this one first, and then something a bit further on. Okay, so if you have cyclohexene and bromine, we form this product here, which is 1,2 cyclohexane. Okay, and obviously the steps in our mechanism: bromine approaches this molecule and is cyclohexene, that is, approaches cyclohexene and is polarized. Okay, so this is just like the alkene mechanisms we do for AS. The attraction between the electrons in the double bond, DB double bond, and Br delta plus is enough for the reaction to happen. Okay, so the double bond breaks and the electrons form a bond with the delta plus bromine, and the bromine-bromine bond breaks and forms a Br minus for the reaction to happen, generating a Br minus and I'm going to put R C plus. R just means anything. So our carbocation, an Rc plus ion. These are then attracted to each other and form a bond. Okay, so we know this mechanism, and okay, so we know this is delta plus, this is delta minus, because the electrons in this bond have been pushed away by the electrons here. So curly arrow there, and then we're forming this compound here with a Br minus. This is plus. Bromine then forms a bond, and we generate, sorry, I should put some arrows in there, our 1,2 dibromo cyclohexane. Okay, nice and simple, easy enough. Right, benzene. What about benzene? Okay, so we talked earlier that benzene doesn't necessarily do these reactions. Okay, so benzene electrons are delocalized. Okay, so that's what we talked about, those models and stuff. This delocalization means when a Br2 molecule, when bromine comes near to benzene, this is not polarized as much. So it doesn't have as large of an instantaneous dipole as with cyclohexene. Okay? There is therefore insufficient attraction for the double bond to break. Okay, so that double bond needs to break for us to form this bond between C and Br. There's not enough attraction between those electrons here and this delta plus bromine here to break that bond. Okay? So there is no reaction. Okay, so in brackets we can say, if you have benzene, so we've seen we can brominate it. So the halogen carrier, we've already kind of discussed this, generates Br plus, which has enough attraction to break the bond. Okay, so when you have a double bond and a completely ionized bromine, the attraction between those two is strong enough that the double bond will break to form a bond with bromine. Okay, but on its own, bromine molecule not going to do it with benzene, because these electrons are spread out more, so they don't polarize the bromine as much. We don't get this attraction for the double bond to break. But there are some compounds that do. So there are compounds similar to benzene which can react. Okay? And one of those is called phenol. And phenol looks like this. It's a benzene with an OH group. And we're going to be looking at phenols in a bit more detail sooner or later. So you add bromine to phenol, and you will get a triple substitution. So phenol really likes to react with bromine. Okay, and then we have 3HBr. Okay, so I could have drawn those hydrogens in green there, because those are from these original sites here. Okay, so why does it react? Why does phenol do this and not benzene? Sorry. Why does it react? Well, the most obvious difference between phenol and benzene is an OH group. So it must be to do with that. Okay, so it must be to do with OH. Yeah. If there's no OH, there's no reaction. When we have an OH, there is one. Okay, so we're going to draw out our model and we're going to look at the orbitals. Okay, so the OH has a lone pair. It's got two lone pairs, but there's going to be one we're particularly interested in. And one of those lone pairs is sitting in a p orbital. And that means the p orbital can overlap with the system of pi electrons in the benzene ring. So we drew our original benzene ring system looking a bit like this. With a delocalized region above and one below. So I can draw that in now. And with our lone pair on oxygen, what happens is that lone pair adds to the system. Okay, so we get this extra overlap here, and the delocalized electron system extends onto the oxygen. And the lone pair of the oxygen is now in this delocalized system. So what we have, instead of a system with 6 electrons, we've now got 8. And that is the difference. So delocalize over this area. Instead of having 6 electrons, you've got 8 with only a slightly larger area that they're spread out over. Okay, so what can we say? Lone pair, LP, occupies a p orbital on oxygen. This overlaps with delocalized ring. Okay, so we said there now 8 electrons in the ring, and what that means is this will polarize a Br2 molecule more, essentially. If you've got 8 electrons as opposed to 6, the Br2 will be polarized more, and it's more than benzene, and enough for a reaction to happen. Okay, so phenyl, its extra electrons can react with bromine. Benzene, because the electrons are really spread out, can't. And then cyclohexene, because the electrons are localized just in a double bond only, it can.